This is fundamental problem 13 from chapter 13. We want to determine the constant angular velocity theta dot of the vertical shaft if the angle phi is 45 degrees. We are to neglect the mass of the cables and the size of the passenger. So I have a passenger here, that's this passenger here. This distance is 8 meters and this distance is 1.5 meters, as you can see from the diagram. And we have theta dot here. The first thing that we need to do is to determine the radial direction, and for this problem, the z direction. And kind of helps us that they have shown theta dot here. So the rotation is like this. And going from the axis to the passenger, that gives us the radial direction. And along the axis, we have the z direction. Now, before we take a look at Newton's second law, I would like to determine the forces that are acting on this passenger. You can do it for either passenger. I chose to do it for the passenger on the right in the figure. So we have the passenger here. We have a force of gravity acting downward on the passenger, so that force is m times g. And we have a force acting along the cable. That's the force of tension, so we'll call that capital T. And those are the only two forces acting on the passenger. So now I take a look at Newton's second law for cylindrical coordinates. I have the sum of the forces in the radial direction is equal to the mass times the acceleration in the radial direction. I have the sum of the forces in the transverse direction is equal to the mass times the acceleration in the transverse direction. I didn't draw the transverse direction on my diagram here because it would be going into the page. And there are no forces going into the page. There are no components of forces going into the page. So we're going to look instead at the sum of the forces in the z direction. That's equal to the mass times the acceleration in the z direction. And just like when we did the normal and tangential components and the binormal, also we have three equations here, but generally we only need two out of the three equations. So in this case we're doing radial and z. So that means I need to break up the force of tension into a radial component and a z component. I know this angle is 45 degrees, which means this angle is 45 degrees. This angle here is also 45 degrees. So if I break up this force into components, I have t times cosine of 45 degrees and t times sine of 45 degrees. Those components, though, are equal to each other because cosine of 45 degrees is equal to sine of 45 degrees. So let's start off then looking in the radial direction. And I go back to my equation sheet and look at equation 1232 to figure out what the radial component of the acceleration is. And then remember the radial direction is pointing outward, so like this. So when I sum up the forces, this is minus t sine of 45 degrees because that force is pointing back towards the origin. And this is equal to the mass of the passenger times the radial component of the acceleration, which is r double dot minus r times theta dot squared. Now let's go back and look at the problem. So we're looking for the constant angular velocity if the angle is 45 degrees. So if it's a constant velocity, then this angle here is not changing. If this angle is not changing, then r double dot, which we have here, is equal to 0. If this angle was changing, which would be the case if the passengers were speeding up or slowing down as they spin around, then the radius would change because as this angle changes, the distance from the passenger to the axis here changes. But because it's a constant velocity, constant angular velocity, r double dot is equal to 0. We know what R is, or we can figure out what R is. So R is equal to 1.5 times, so that would be the distance from here to here, plus we need the distance from here to here. If this angle is 45 degrees, that would be 8, which is the hypotenuse, times sine of 45 degrees. Which gives us 7.157 meters. Okay, and then I'm looking for theta dot. I don't know what the tension is, so we'll just bring this down here and say minus t times sine of 45 degrees is equal to the mass. I have this negative sign here too, so I can make both sides positive, times the radius, which is 7.157, times theta dot squared. So now I have one equation and 3 unknowns. So next, I'm going to look at the sum of the forces in the z direction. So in the z direction, I have t times cosine of 45 degrees, and then when I sum up the forces, mg is pointing in the negative z direction, and this is equal to the mass times the acceleration in the z direction, which you can take a look back at equation 32 in your equation sheet, but the z component of the acceleration is just z double dot. Now, if this angle isn't changing, we said r double dot was equal to 0. If the angle isn't changing, not only is the distance from the axis to the passenger staying the same, but the height of the passenger isn't changing either. So z double dot is equal to 0. And we can say also r double dot is equal to 0 because we have a constant angular velocity. If it's a constant angular velocity, that means theta double dot is equal to 0. So if this is equal to 0, that means t cosine of 45 degrees is equal to m times g. But t times cosine of 45 degrees is equal to t times sine of 45 degrees, as we said before. So now let's go back to this equation here, and we can use both of those equations and say t sine of 45 degrees is equal to m times g, and that's equal to m times 7.157 times theta dot squared. And now the mass cancels out, and we can breathe a sigh of relief because we weren't given the mass of the passenger. And so then to find theta dot, we have theta dot is equal to the square root of g, which is 9.81 times 7.157, and that should not be multiplied, that should be divided by when I bring it over to the other side. So 9.81 divided by 7.157, and then taking the square root of that gives me theta dot, which is 1.17 radians per second.